So, welcome to Structural Concepts. In this class, there are no textbooks. So anything you need to do this class, we posted up to Blackboard. Same as all my other classes, there is a test on the syllabus. You should know the drill by that. What I'd like to talk a little bit about is on the design team. What's my purpose of teaching this course? Am I teaching you so that you can go out and say you have your own business like Tim does designing houses, or say you're in a situation where you're in a design firm? Am I teaching you these concepts so that you can size your own structural members on your projects? And so I'm going to talk a little bit about who designs structures on a design team. And in order to do that, my first thing I'd like to talk about is a scenario where we're going to do a role playing and you're going to be the jury. And what I would like you to do is pretend you're the jury and this is a potential lawsuit. And our scenario is it's a custom single family house with a bouncy floor and cracked tile over the beam. So it's not like the house fell down, and pancakes some people. It's what normally happens in this country if you have a structural related issue that could you guys quit clicking your mouse just for a second? It's kind of distracting my train of thought. Can you get at least to a place where you can stop clicking the mouse and then stop? But when we get to a case where the structure maybe is undersized, but it's not immediately dangerous. And this is kind of based on a true story. So in my first job, my first day on it's actually my second job. My first day after I got out of grad school, I walked into my new job and everybody was in an uproar because a client was threatening to sue our company because they had cracked tile over a floor beam in the house. And that can happen for a couple reasons. They thought it was happening because the floor was sagging or the beams were deflecting enough that this very thin, brittle marble tile was cracking. But it turns out it was because of shrinkage. Remember I told you that wood shrinks because of the moisture in the air and steel doesn't? That column was held up by a steel column. The rest of the house was shrinking and the beam wasn't shrinking. But they thought originally it was structural. And I found out that this firm that I'd been hired at didn't hire somebody outside of the company to size their structural. We did very fancy custom houses. I shouldn't say fancy, but we did complicated custom houses. And they didn't hire somebody like a structural engineer to size their beams. They did it themselves. And so they were all up in arms because they wanted, the people had a lawsuit where they were like suing for the repair and they were also suing for like loss of use of the house and everything. And they were threatening the lawsuit. And that's my first day of the job. I walked in on that. So our scenario is somewhat similar. In this case, the floor is actually bouncy. So like, have you ever gone in a house where you walk around and you can hear the dishes rattling in the china cabinet? That's a sign of a house it's not probably going to hurt somebody, but it's not meeting your expectations. So when you go into a custom house, you don't expect the floor to bounce when you walk around on. You don't expect the dishes to jiggle in the china cabinet. So what's happening in this case, we have one scenario where the designers designed the house and designed the size of the structural members themselves. Okay. So I'm going to teach you enough information that you can go through if you were designing a house and you could size all the structural members yourself. Okay. Now that's the first scenario. So what's going to happen is the owner's going to get up and they're going to explain, they went to this custom home designer and that they thought they were going to get a good quality house. They're paying for a custom house. They're paying for a custom design. And their expectations were not to have a bouncy floor and cracked tile over the beam. Now they've got to repair the beam. They don't feel good about their house. So they're wanting $20,000 to fix it and $20,000 for emotional damage. So if now let's pretend I'm the designer. When I get up there, what kind of questions are the owner's attorneys going to ask me?
You seek out a structural engineer to verify your work.
Yeah. I would, if that's what an attorney, or the other thing, what other question could they ask? That's an excellent one. That's, yeah.
You're like, you're a certain type of inspection or who wants to inspect your.
Yeah, you could get an expert witness to come in and look at it and make sure that the beams, were in fact undersized. The other thing they might ask is, well, who sized the structure on the house? And as a designer, I'd say, well, I did it. I took a class with this guy named Pete, and he showed me how to do it, and I designed it. And then they're going to ask, okay, how much else training did you have? Structural engineers go to school for 4 years. You had one class for 7 weeks, and you think now you're capable of sizing things. And so what do I say to response to that? Well, Pete's a nice guy, and I think he told me how to do the right things, and I think I remember it. Okay, so you're the jury now. My strategy would probably be to blame the builder and blame the lumber supplier and blame the tile supplier and blame the tile installer. Because if there is a lawsuit, the way these things go is everybody blames everybody else, regardless, because they're just trying to share the blame. So I would probably say, well, the tile installer installed the tile wrong, and the contractors maybe didn't use wood they used wood that had gotten all wet, and this isn't related to sagging, it's more related to warping. I would just make up or come up with other theories on what it could go wrong. But if you're the jury, now let's imagine you're the jury. Who would you find? You could find anybody liable. Like you could find the tile installer partially liable and me partially liable. Or you could find nobody's liable. It's up to the owner to fix it. So what would be anybody's thoughts? Imagine you're on the jury, what would you say to the other jury members on who you think should pay the cost of this? Who would be responsible?
I want to know if the builder followed the plans to code or to the drawings.
Yeah,
I want to know if there were inspections done by
Like
both parties
Yeah.
to see how much it would actually cost to fix it.
yeah. Yeah, so those are all good things. But who's probably going to end up being most liable in the jury's mind? Any guesses?
You for designing it.
Yeah, because I'm the one that actually designed it. Now I can try to default, you're exactly right. They would do all these tests, they'd have expert witnesses look at it, but I would be responsible. So now we're going to think of a second scenario. So when I started coming into this company, I said, you know what? Our houses after I heard about this whole scenario, I said, our houses are more complicated than some simple commercial buildings are. Because they're 2-3 stories and they've got floors that commercial buildings, a lot of times they're dead not simple. They're like one floor stacks on the other floor. I had floors that were different sizes on floors that were, smaller floors on top of larger floors. So I had to have point loads coming down. I had cathedral ceilings. It was more complicated than some of the commercial projects I had worked on. So I said, hey, let's just go hire a structural engineer to do these complicated houses. Because the owner is paying us or the structural engineer, and why don't we hire somebody that does this every day, all day for a living? And they're like, well, who should we hire? I'm like, well, Arnold Sheridan is the biggest structural engineer in Madison, and they probably have somebody that's just an expert at wood. And let's at least find out how much it is. So we went and talked to Arnold O'Sheridan, and it turns out that they had a guy that's all he did was focus on wood structures. Okay, he was an expert at it. And he was so good, he could do it so fast. He had so much good software and so much experience. He could do it for, I think it was like a couple $100 on these. No, this was 30 some years ago, but he could do it for a couple $100. And, we were spending 2 or 3 hours at, I don't know what the billable rate was back then, let's just say $70 an hour. So the owner was still paying about a couple $100 to have an untrained person doing it, where we could spend a couple $100 and have an expert that could do this stuff in his sleep do it. So now let's imagine that scenario, and there is a problem with the house, and we do get taken to court. As a designer, what am I gonna say? I'm gonna say, I hired the best structural engineer in Madison with years of experience. And so I did my professional duty. I hired the best possible consultant I could hire. And then what the engineer's going to say is, let's just say on the off chance that this expert made a mistake. Well, they're probably going to be the ones that are most liable, because it wouldn't be me, because I hired them and I'm paying them money to do this. Okay. So people ask me all the time to give them structural advice on their house. They're like, hey, I'm going to take out this. My wife and I want to open up between the dining room and the kitchen. Can we take this wall out? I'm like, I don't know. You got to get a structural engineer, because I don't want to, even if I don't think it's load bearing, even if I'm almost certain, I don't want to take that liability on myself. Right. So I say, you got to get a structural engineer and look at it. So then what typically happens, and they call up a structural engineer and they're like, they said they would come over and look at it for an hour and do the calculations and get me the paperwork, and it was going to be $700. $700 for an hour. What a ripoff. What they don't realize is not only are they paying the 1 hour at a time, which might be $150 or $200 for their hourly billable rate, they're paying for their liability insurance, because by giving them that little report on that one beam, they're taking in all the possible liabilities. So they have to pay for expensive insurance to cover them for that. Okay. So that's why typically you want a structural engineer. This is one where I got specialization here. You want a structural engineer that specializes. If it's anything other than a very, very simple project, it's a good idea to have a structural engineer look at it. I'm here. Tim is doing some house designs for like the wood tech project, and they had to have a beam size, and Tim doesn't size the beams himself. They're working with a structural engineer to size that, and a lot of times house designers will put disclaimers right on their plans. These were not, none of the beams or structure was sized. This needs to be confirmed by a trained professional. And a lot of times on a house, the lumberyard ends up sizing this stuff for you. Those of you who work construction on houses, most of the time they have a designer that works for the lumberyard, but it's typically never the home designer that takes that liability on themselves. So it's just like when you need surgery. I needed some minor surgery on my arm, and the person that was doing it was like talking to me about golfing and talking to me about fishing while they were cutting it into my arm. And he left the room for some reason, and the nurse, and I'm like, is this guy even paying attention? I was talking to the nurse. She's like, trust me, your simple little surgery, he could probably do this blindfold. He's done hundreds and hundreds and hundreds of these. He does not need to just speak. This is just like sharpening a pencil to him. It is not super complicated. So you want somebody that does it all the time, every day. They've got experience. And so we're not teaching you in this class with the thought that you're going to go out and design structures. But we're teaching you, first off, so you can communicate people that do design structures. And secondly, when you're doing your preliminary design, you need to know like how buildings go together, the rules of it, how the structure works, so that you don't design something that's unbuildable or super expensive to build, because you know these structural concepts. You know that you need beams columns every so often. You need beams, how the beams work. So we're kind of giving you a background, but we're not turning you into structural engineers. Structural engineers is like 4 years of college, taking tests, all this other stuff. Okay, so this isn't a structural engineering course. You should not go out and size all your own structures if you decide to be a house designer, in my opinion. I think you're better off hiring a professional, because the owner is either paying you to do it or paying somebody else to do it. but they're not paying that much more to have somebody else and take all that liability. But some people don't get this through their thick skulls, so this is item 2B. So say some people are like, well, look, the owner's gonna pay $1,000 to get the structure done on the house. I can either do it myself and I can keep the $1,000, or I can give it to the structural engineer and I don't get anything off of that. So I'm just giving $1,000 away to the structural engineer. I'm gonna design it myself. What they don't realize is they're taking all that liability, especially if they don't know what they're doing. And that's worth a lot more than $1,000. Any of you ever had anything go wrong with a construction project? $1,000, that's like loose change that you get out of your couch if anything goes wrong seriously with a construction project. Now, does that all make sense as my background? So what you should get from this is this 1 7-week class does not make you a trained beam designer or structural designer that you should feel confident going out and designing things. So what I'd like to do on my first kind of get you into the life of a structural engineer, I want to show you a little video about the life of a structural engineer. And this is interesting for a couple ways. It's interesting because it's set in Australia, and it's going to show you that once you get trained in this field, the skills you learn and the concepts you learn are applicable if you decide to leave USA and work somewhere else. Okay, because they're still using Revit over there, my guess is. And they are building houses, and the structural forces, there might be a little tweaks, but the structural forces, they're still doing beams and headers and columns and I joists, and all those things are still the same in other countries. So let's go ahead and watch this.
Hello, my name is Adam Ferrari, Chief Executive Officer of California, here joining us in our
Okay, now why I had this all figured out and why is it not working? So I got to go through this whole rigmarole again. Extron and NVIDIA, let's try this. Yeah, okay. So now I'm going to skip this stupid commercial.
This is the day in the life of a structural design engineer in a buildings team that designs high rises all the way down to residential houses. The office I work from is based on the east coast of Australia, but before I show you my day, let me.
First thing to take away from this is if you ever get a job offer on the east coast of Australia, take it. Because when I look at this and I look at where he lives and the beauty of it, I think this would be a great place to work. Plus, you wouldn't have to learn another language. Okay, so let's get going.
In December of 2021, I graduated from a degree in civil engineering, and shortly after began working at a big local design company. At this company, I worked on various steel frame structures and got my first real taste being a full-time engineer. But after a year of working at this company, I decided that big corporate lifestyle wasn't for me and that I needed a change. So I touched up my resume and started the job hunt for a new role at a smaller company. During this process, I reached out to quite a few people who work at smaller companies and even got in contact with one of my old university professors who ended up passing on my resume to one of the nearby small engineering companies. Soon after my professor did this, the company reached out, I sat an interview, and I eventually got the job offer.
Just a pause. I do not ever give your resume to people. When somebody says they're looking for something, I will keep you in. I have to treat everybody fair. I can't cherry pick. Well, I think they'd be great for this company because I like this company, so I'm going to have them go there. I think these people are bozos, so I'm going to send them to these people that didn't treat me right and I didn't like them. I don't do that, okay? So what I do is that somebody says they're interested in our graduates, I send an email to all of you and I let you contact them. I do not first off, I can't give in this country, I can't give your information to people without your permission anyway. All I can do is let you know of availability. So just to clear that up.
My day. In the morning, I always start my day off the same. I begin by having a quick shower, getting dressed, and making myself some breakfast. For breakfast, I usually have a bowl of oatmeal and some toast, and while I'm eating, I usually like to watch something on YouTube. After this, I head over to my desk and begin the workday. Today, I'm going to be starting the day working from home as I've got a site inspection I need to go over later this morning, and I'm going to do it on my way into the office. As a structural engineer, it is pretty typical for me to work in a variety of places, so that means some days I work from home, On others, I'll be in the office and outside. And some days like today, it's a mix of all three of these. Anyways, the first thing I like to do when I sit down on my desk in the morning is open up my iPad and create a to-do list. The app I use to write my to-do list is called Notability, and this process usually involves carrying over any tasks that didn't complete from yesterday, adding new tasks based on yesterday's progress, and then ordering this list by whatever is the highest priority. After this, I'll open up my work email with Microsoft Teams and catch up on anything that's been sent. I signed off the day before. Sometimes after reading these messages, I've learned to add more tasks and reprioritize, but today I was lucky and I didn't have to. In the morning while my brain looks fresh, I always try and jump straight into design work for a couple of hours. Right now, the main project I'm working on is a steel portal frame building for a sports hall. And for the last couple of days, I've been setting up a space gas model, which is going to help me do the design for this project. Up until this point, this process has involved me doing things like inputting geometry, node restraints, and member properties, working out the wind loads using hand calculations and Excel spreadsheets, and also inputting all my load cases and combinations. And now finally, after all this prior work, today I'm going to be analyzing the design actions from this model so I can start sizing the members. Right now, I'm going through each of my load cases and checking things like deflections, bending moments, and shear forces, and trying to find which of my load cases are critical. Nowadays, most structural analysis programs also include a design or check feature, so after I've done some sanity checks for sizes that I think work, I'm going to run the check feature and make sure that the software also agrees with the sizes I've chosen. Now, like I mentioned earlier, I do also have a site inspection I need to get to this morning, so it's time to stop working on this project, pack my bag, and get on my way. In the office, I pretty much have a full setup minus my laptop, so I only need to transfer a couple of things with me. First, I have my big Dell work computer. Next, I have my trusty 11-inch iPad Pro and Apple Pencil. And lastly, my calculator. I'm also planning to head to the gym after work, so I'm going to quickly pack and change clothes for this too. And of course, because I'm heading to site, I'll also need my steel cap boots and hard hat, tape measure, safety glasses, and a high-vis vest. But I usually keep that stuff in my car ready to go. Today, the site inspection I'm going to be going to is a house framing inspection. And lucky for me, this one isn't too far away, so it's a nice, easy drive. When I get to site, the first thing I do is change into my work boots, grab my iPad, and put on my hard hat. After this, I'm ready to go and start inspecting. Now, during a framing inspection, what I'm doing is checking down.
I'm just gonna pause here. Those of you that have done construction, and you can see there, they still have joists, whether they're ceiling joists or floor joists. They still have headers. They still have studs. So the skills that you use here are not just usable in the United States. Now, in some countries, their building technology is a little bit different, but there is a lot of countries around the world that use the same software and the same concepts. And obviously a floor plan is a floor plan, wherever you go. So you're not just getting trained for a US specific job. If you wanted to open your mind and work overseas, what you're learning here will transfer.
All aspects of the timber and steel frame are as per the structural drawing. So that means that I need to start at the ground floor and check the wall and floor framing, then eventually go upstairs and check the roof framing. During this process, I'm checking things like
So you can see their trusses just look like our trusses, same gang nail plates. You'll notice they did a little combination of steel joists and steel beams. There must be an addition to an existing house on this one. This just reminds me a lot of Florida with the canals and the palm trees and everything.
size, grade, and layout, the connections and tie downs, and also that enough bracing has been installed and in the correct locations. When I'm going around and checking all these things, I really
Your hand up or you're just stretching.
try to be as thorough as possible because inspections truly are the last line of defense, as anything that's not flagged during this final check could result in a structural failure. A two-story framing inspection like this usually takes me about an hour and a half to complete, but by the end of that time, I feel confident that I've checked everything properly. After finishing.
So the inspections, then you had mentioned inspections a couple times, Todd, right? Inspections are important at certain times in the project. Now, the cities and the governments around here, depending on where you're building a house, they might send an inspector out like before you drywall it, so that it's like a rough inspection so you can see that everything's done properly. But if you've ever built a house out in the boonies somewhere, some of these counties, nobody will ever show up on the job site. So you had mentioned, did they do inspections? A lot of times the government will not do inspections. There's just not enough inspectors for all the job sites to get out there. But here in La Crosse, they will inspect it quite often. So the other thing to think about is you can have all the drawings done right, but if it's not built that way, there's gonna be problems, and it's better to catch it before it gets drywalled. If there's only 2 plies in the header and there should be 3, or if the joists have got the wrong spacing on them, or if there's not enough nails on something, it's a good idea to have your consultant come out there and look at it. Now, the problem is, a lot of times, the owners don't want to pay for the inspections. So say you're doing an engineer that say that they're working in Eau Claire or whatever, because they're a good engineer and you've got a relationship with them. The owner, you're gonna have to convince the owner that it's worth their money to pay for that engineer to drive 2 hours, look at your house for an hour and drive back. So that's always kind of a negotiated thing. Now, on a commercial building, we would typically build in engineers inspections at critical points, because just to cover everybody's butt, that has to be on our fee. So like before they pour the concrete, we want the engineer out there making sure all the rebar's in there. So anyway, let's keep
The
going.
inspection, I now need to write a site inspection report which details anything that the builder needs to fix or change. This is usually a pretty quick process, as throughout the inspection I've been taking notes of all the
So a couple things, when you do an inspection, take pictures like crazy. Because with digital cameras, it doesn't cost you any money to take a lot of pictures. And those are super valuable if anything ever goes wrong and you get blamed for something that wasn't installed properly. You could say, hey, I got a picture, it was installed properly. And then the other thing is that they're taking the notes immediately afterwards, because I guarantee you, if you're like, oh yeah, I'll write this all up when I get back to the office, somebody will cut you off in traffic and you'll get pissed off, or you'll get distracted and go out to lunch or something, and you'll totally forget what you're supposed to write down. So he's being smart, writing down the notes he needs to do immediately in the car while it's fresh, before he loses track of what he's doing.
these things.
Yeah.
I guess clarification, are you speaking from as if you're a structural engineer, or are you talking about as a designer, like?
Both.
Both,
I
okay.
take pictures all the time when I'm out on the job sites.
So how often do you go out to the job sites?
Again, it's a matter of, there's kind of a balance. If you're working for, so like I've done work where the owner hired me and my company to design their house. I've also done work where I was doing it where the contractor hired me. It's a design build situation. When the owner hired me, they still had to pay for me to go out there. So I had to convince them, or my boss had to convince them, that it's worth doing 2 inspections or an inspection every month, because you're going to end up with a better project. Because we're not going to do it for free. We need to get paid to go out there. What I found was, as my bosses started to do more design build, where the owner's contract is with the contractor and the architect works for the contractor. The architect doesn't work direct for the owner. And then the contractors didn't want me on site. So they were just like, they only wanted to pay for the minimum. The state, I think, on a commercial building requires a minimum of 1 or 2 inspections by the designer. And that's all they wanted to pay for. They did not want me on the site. They didn't want to, because it's coming out of their profit, right? Because the owner's paying them a lump sum. And every time they have to pay to me going on the site, that's just less money their company gets. So they would only want me to be on site for the bare minimum. They didn't want me to be on site, because what happens when you send somebody like me on a site? I can't turn it off. I'm like, oh, that's installed wrong. That's screwed up. That's screwed up. And now they have to pay to fix all that. Where if I'm not out there, maybe nobody catches it. Nobody cares. Okay. So they wanted to minimize but the state still requires a minimum. I think it was 1 or maybe 2 that the designer has to do a job site inspection.
For both commercial and
For
residential?
commercial. For residential, it's like the Wild West.
Okay.
You can design the plans and never go out on the job site. It's all convincing I tried to convince the owners, like when I sat in these meetings, that it was in their best interest to pay us that couple $100 to get us on the site, because we can catch things and they're going to end up with a better project, and it's quality control basically. Yeah.
I guess since we're like studying to be more craftspeople and maybe other architects, would we even like really have the authority when we go to a job to like say like to give like inspection advice, or to even?
Well, you got to be, so I started out not an architect, but I still did job site inspections, because like I was the one that did the design. I was the one that did the drawings, like for houses. Like my first projects were on houses. And I was the most qualified to go out on site, but I didn't, when you say you go on inspections, basically what you do is you document the issues and then you take it back when you're starting out and you show it to your boss and they decide if this needs to get run up the ladder. So the last thing you want to do when you're on an inspection is like, hey, that's all done wrong. You got to tear that off. That's not going to work, right? So what you typically have to do is document, show them what the problem is. And if it's a good contractor, they'll be like, oh my gosh, yeah, that is wrong. Once they see the documentation, you just give them a report of what you saw. You could say, this needs to be verified. I'm not sure of the nailing pattern on this. I'm not sure that these are the right fasteners. I'm not sure that they used galvanized connectors on pressure treated beams. So you're just noting all this stuff. And where it gets, you don't go out on the job site and say, hey, tear that off, that's wrong. You're not the boss of the contractor. You're just doing the inspection for the owner. And when you give the contractor a copy, if they're a good contractor, they're like, oh my gosh, we missed that, thanks so much, and we'll fix it. If they just say, screw you, we're not gonna fix it, then that's not at your level anymore, right? As a beginning employee, that's your boss's level, and that's the owner's attorney's level, and that's the contractor's attorney's level. You don't ever go out on the job site and start telling people what to do.
Yeah.
That's
So it's
never
really
done.
just like gathering data.
It's gathering data. It's just an observation. A lot of times our attorneys didn't like us to call it a site inspection because we were just doing a site observation. So the word inspection was never on our report. It was just us observing what was out there. We weren't inspecting it because inspecting tends to mean like, I looked at every nail to make sure it was the right, I didn't do that. I just observed, and these are my observations. Yeah, go ahead.
So if you're doing the residential, would it be in your best interest to like, when you have like your lawyer drop your contract or whatever, like with the potential client, that it's included? That if you don't include site observations, then I am not liable for
Yes.
any,
Yes.
stuff like that.
Sounds, yeah. So you can say that and I've seen contracts like this, my liability is limited to what you paid me to draw up these plans. So again, I wish I lived in a world where nobody ever threatened to sue people and nobody ever got sued, but this is America and that's not the way it works. When things go wrong, and the other thing is that I found out in my personal life is that, or my professional life, is that people with money use attorneys to bully other people, right? Remember when you were in grade school, the big, strong people bullied the wimpy, skinny people like me? Well, it's just like economically, the big, strong, wealthy people bully the poor people by hiring, and they use it by hiring attorneys to bully them, right? So if you have enough money to hire enough attorneys, you can basically make somebody else's life a living hell until they give in. So that's like bullies. So thinking about liability, what we do has liability implications, right? So if you do something wrong and somebody suffers because of it, economically, physically, materially, they're probably going to ask you to make it right. And if you don't, there's going to be some sort of lawsuit. That'll make sense?
And from our previous conversations, you had said once an issue is found, you're liable up to 7 years
Yes,
after
okay.
it's found.
Yes, I think so.
Okay.
That's the way the law was when I was, thinking about all these things. Now, are lawsuits very common? No, they're not. Because what happens, I can guarantee you who wins in a lawsuit. It's not the owners guaranteed to win. It's not the defendants that are guaranteed to win, like the architects or the contractors. It's the attorneys that are guaranteed to win. Because what happens is when there's a lawsuit, everybody hires attorneys and they get paid whether or not you win or not your case. So you're going to spend many, many thousands of dollars. Everybody's going to hire attorneys and they're all going to finger point at each other. And then the attorneys are going to make money, $500, $1,000 an hour arguing among themselves. So what typically happens is, hey, look, none of us want to go to a contract because we're lawsuit because we're all going to lose money. So you would get together because we're all going to pay our attorneys. So you get together with a contractor, you get together with the owner, structural engineer, the material supplier. So in this case that I was talking about, remember when I walked into the job, we got together with the tile supplier, we got together with the contractor, we got together with a design firm and we said, look, nobody wants this thing to go to a lawsuit. First off, lawsuit, bad press, tell your neighbors. I had to sue them to get them to fix this. We want happy clients that are going to recommend us. So we're like, hey, we're going to make this right. So we had a big meeting and like the tile person said, hey, I'll give you the replacement tile at my cost. No markup, just replacement tiles at my cost. Tile installer said, yeah, I'll reinstall it at, no markup, bare minimum just for my materials. We said, okay, we'll kick in X amount, to take care of paying the tile installer or whatever. The contractor said, okay, we'll do this for free. So we all kind of kicked in and got the project solved. The client was happy. No attorneys had to get hired. And it was cheaper for us and the client's happier, we're happier, everybody's happy. So that's typically, these things get settled. The lawsuit's typically just a threat to get some action going on. And once that action goes on, typically it doesn't end up going to trial. Does that all make sense? Okay, so let's keep going here.
Down on my iPad. Anyways, now that this site inspection is done and it's roughly 12 p.m., I'm going to stop and grab some lunch. After a quick bite to eat, it's now time to make my way to the office and get some more work done.
At Full Sail, our technology programs are designed with a different approach to learning. We let our students get hands-on and start
When I get to my desk, the first thing I do is upload my things and get myself set up. This afternoon, the first task I'm going to be doing is going through some drawings that the drafting team sent back to me for review for a small granny flat that I designed last week, just to give you some context for those of you.
Okay, so if you were working in Australia, you might be his drafting team. You could get a job once you graduate from this program as a drafter at a structural engineering firm. Okay. So people that have, all the years of college and everything, they're not sitting at the computer doing everything themselves because they've got other projects they're working on. So it's more efficient to have a more entry-level person doing the drafting. And then what happens is somebody like this, who's got the engineer's degree, looks over your work and red marks it just to make sure, because they do the quality control before it goes out, but they don't sit there and figure out, plunk everything in on Revit or whatever software they use. Okay, so when he's talking about the drafting team, that would be potentially somebody like you. He would mark up exactly what he wants done. You would do it, print it out, give him a PDF, whatever it is, and then he'd review it because he's the one that's putting his stamp on it and taking the firm's liability. It's not you as the drafter that's taking the liability, it's the company, the people that are in positions of authority.
of you that are unaware of the design process that happens in a structural engineering office, it looks something like this. First, the engineer will receive a copy of the architectural drawings and the site soil report. Second, the engineer will do their calculations and analysis using hand calculations of various software programs. Third, the engineer will illustrate their design. What this actually looks like is just 2D shapes and annotations over the top of architectural drawings, which show the different structural members and the layouts they want. During this process, the engineer also needs to illustrate the connections and any other structural details throughout their design, so that eventually the builder knows exactly what to do. Fourth, the engineer needs to send this illustration, or what is more commonly referred to as a markup, to the drafting team. Fifth, the drafting team draws and models what we have marked up and sends it back to the engineer for review. Sixth, the engineer reviews these drawings and makes any further comments they have on the drawing. And just for reference, this is what I'm doing now. Seventh, this back and forth process between the engineer and the drafter continues until the engineer is happy with the drawings. Eighth, the drawings are peer reviewed by a senior engineer. Ninth, any changes indicated by the senior engineer will need to be amended by both the design engineer and the drafter. And finally, number 10, the structural drawings are issued to the client. While this does sound like a really long process, actually doing a review of a design you've marked up doesn't take too long, and that's good for me because I need to move on to my next task, which is doing a shop drawing review for a factory another engineer on my team has designed. A shop drawing review is basically just reviewing the model and drawings the steel manufacturer has created based on the set of design drawings they have gotten from us, and just double checking that they have interpreted our design correctly before the steel items are manufactured.
Okay, so this is another potential job you could get. So let's say, is there Mid-City Steel or somebody around here?
Yeah.
So when we do our drawings for a building, they don't just take our drawings and put them down in the factory and try to figure out where the bolts are and exactly how long all the individual beams are and start cutting steel. Okay. So what they do is they do drawings for their factory or their shop, as it's sometimes called. And those are called shop drawings. So somebody like you would take the architectural drawings and you would know exactly how, you would figure out exactly how long to cut the beam, if it has to be notched out or to get around some other column or something. He would show exactly, you do a drawing and dimension, exactly the diameter of the holes for the bolt, exactly where the bolt locations are, because that's what they're going to use on the factory floor. Okay, so you've done your shop drawings, but they don't just send them right to the factory floor to start to build them, because what if they need to make sure that it still complies with what the engineer drew the first time. So like they might read something wrong and put not enough bolts in or something. So what happens is the shop drawings go back to the engineer that looks at it and says, yes, this is, they don't verify the dimensions, but they're like, structurally, this is what I had showed them. It meets the design intent. And that's what he's doing now. He's reviewing those because we did the design firm's drawings. They did their shop drawings. They send it back to the design firm. They approve it. And then they go ahead and start building it. Oh, the other thing that happens is in addition to going to the design firm, it goes to the contractor. Because what does the contractor need to verify? If we told them that these columns were 20 feet apart, they're going to design the shop drawings for columns that are 20 feet apart. The beam's going to be 19 feet, 8 inches or whatever it is. But let's just say on the job site that when they poured the footings, they were 3 inches off, and now they're 20'3" apart. If we don't have it verified on the job site, those beams are going to show up and they're not going to fit. Okay, so the design engineer approves it first for design intent, then it goes to the contractor who marks up all the dimensions based on the site conditions. And then it goes back and then they finally build the things. Now, what happens when things go wrong? I worked on a project with a young engineer and he thought it was his job to mark up the dimensions, even though he hadn't been on the job site. So he changed all these dimensions, red marked the whole thing. And I'm like, if I hadn't looked at this, because I had him send it back to me and then I looked at it before I sent him back to the contractor. If I hadn't caught this and brought it to the attention of his boss, there would have been like a football field full of steel that was all the wrong dimensions that the engineering firm would have had to pay for. Because he had taken the liability on himself, being clueless, thinking he was doing a really good job, and he changed all these dimensions and he was going to send it back to the steel fabricator. There would have been like hundreds of steel beams, all the wrong dimensions that they would have made based on his markup, and it would all been his company's fault to pay for all that. Okay, so you hear this, you don't realize how complicated buildings are until you get into it. So there's a lot of stuff to learn. There's a lot of complication. There's a lot of checks and balances. Look at all the checks and balances inside the office. He checked it, then his boss checked it, then the drafters do it, then he checked it, then the boss checked it. Now the shop drawings, those are more checks. So that's how we avoid having problems and having things not being done properly.
This may seem like a straightforward process. It can be a costly one because it's the last chance we have as a designer to make sure that things are going to be made the same way we have designed. Anyways, it's around 5:30 p.m. now, and I've finished most of what I want to get done today, so I'm going to leave the office and head to the gym. The gym is about a 10-minute drive from the office, so I like to head there straight after work a couple of days a week. At the gym, I mainly do strength training exercises, and I usually spend about an hour there. After this, I head home and have some dinner. Once I've eaten my dinner, I usually get a final look.
Okay, so he talks about how he does the YouTube videos. So let's go back into my agenda here. So what I'm trying to do is give you a knowledge of basic structural principles versus the ability to do calculations. I want you to have the ability to communicate about structural concepts with structural engineers and other people in your office. So believe it or not, some of our graduates do work as structural drafters. Like they did the structural drafting for the Lacrosse Center edition. So they work at ISG and they did the structural drafting for the engineers that worked at ISG that did the Lacrosse Center edition. So they were graduates of our program. Some of our graduates have gone on to get structural engineering degrees. And one of them actually told me that he worked as a drafter and they liked him so much that they said, hey, if you want to go on and get your engineering degree, we'll pay for your college. They paid his tuition. Now, he had to sign an agreement that he'd keep working there once he got his degree for a certain number of years, but they paid for all his college. So back in the day, you had to learn the calculations all by hand to size a lot of this stuff. Right now, most of it's done by computers, but you still, the engineers that are the people that are checking it over, they still know the structural concepts and they could do it by hand if they wanted to, because sometimes the software makes mistakes or people put the wrong number in the software. You have to know enough to know when the software is giving you a wrong answer, that's not in the ballpark. Does that all make sense? But we're not going to learn a lot of, we got a modest amount of math in this class, but I don't make you learn the extreme math to sizes. I do teach you a computer software program to size some of these things. So we have 3 assignments. One is that I'm going to have you watch a video about a design meeting between an architect and an engineer and answer some questions about it. We're not going to do this in class. So this link on item number 7, it's also on my YouTube channel. So if I go to here and I look at the full playlist, structural engineer versus architect design meeting, I want you to watch that video and answer questions. This is an excellent video because it's the most realistic one I've ever seen about if you're meeting with your structural engineer as a house designer or a building designer, how you kind of go back and forth and figure out how this thing is going to be held up. And Tim taught you about sketching. Even though with all the computers, there's still a role for sketching on tracing paper over plans and using it to communicate ideas in a meeting. Because you don't always want to say, well, I want to show you this idea, but I got to go back to my office and draw on the computer for 20 minutes and then I'll come back. It's nice to be able to take up a pen and just kind of sketch up your ideas. So watch that meeting. That's one assignment. The second assignment is I'm going to give you a PowerPoint about the basic concepts of forces, and then there's a test or a quiz on that PowerPoint. And I'm going to try to get that done today. The last one is going to actually be presented on Thursday's class. So I don't know if you've come to the conclusion in your life now. Do you learn more from when things go really well or when you make a mistake and things go really wrong?
Things go really wrong.
I personally learn more when things go really wrong, either in my life or somebody else makes a mistake and it impacts me. I learn more that way. So rather than have us make the mistakes and learn from our own mistakes, we're going to try to learn from the mistakes of others so we can avoid making the same mistakes. So your first assignment, 1.1, which is going to be presented on Thursday's class, and I know you've got classes with Josh in the morning, so I'm going to try to give you some time to work on, is a structural failure case study. So let's show you that assignment. So if you go to assignments on Blackboard, we're on week 1 fundamentals. You can see where we're going. We're going to build up just like a house is built. We start with the footings, we go with the floor framing, we go with the wall framing, footings and foundation first. Then we do the columns and then we do the roof framing. So that's how we're going to go through the class. Let's look at week 1. There's a test on reading the syllabus. There's a forum on structural failure case study building selection. It's first come, first served. And only one person can do that specific building collapse. So like there's one called the Hyatt Regency walkway collapse in Kansas City, a very famous one. I'm not gonna have the whole class do it because that probably is gonna show up on the first page of the Google results and otherwise I'll have 20 people doing it. So it's first come, first served. And what I'm going to do is I'm going to give you some time to pick it up until the break and during our break, and then we'll move on to the next one. So let's just go to talk about the assignment. So you're going to post your building selection up to the discussion board, and you're going to see the other ones that have been approved, and I'll say thumbs up or thumbs down. And then you're going to upload it up to Blackboard. So let's look at this assignment. Let me see if I can get a bigger version for you to read here. Structural failure case study. Here we go. Assignment 1.1. So we want to do a case study of a building. So a case study of a building is not a dam, it's not a bridge. They're not buildings. Buildings are things that people live inside that are not space stations, anything like that. They're attached to the ground, they're buildings. For the purpose of this assignment, a structural failure occurs in circumstances that are not extraordinary and occurs because of number one, faulty design. Somebody screwed up something on the design, or somebody messed up something on the construction. That's a structural failure. So if you shoot a missile at a building and it falls down, that's in a war, that's not a structural failure. Terrorism is not a structural failure. Flooding, earthquakes, tornadoes, hurricanes, tsunami, they are not considered for the purposes of this assignment a structural failure. Yes, the building fall down, but the engineer or the designer or the contractor did not make any mistakes. Will not learn anything from that. If you have a building that fails while it's under construction or being demolished, that doesn't also meet the criteria because buildings are inherently unstable while they're being constructed and while they're being demolished, right? There might just be one nail holding that thing on, and if it falls down on somebody and it hurts them, that's not a structural failure, that's a demolition failure. If something happens during construction and the crane cable breaks and it falls down, that's not a structural failure, that's a construction failure. Does that all make sense? Building that fails because of a problem, because of design or because of construction. So you're going to select your building, post it on the assignment 1.1 discussion board. It's first come, first served. The building must have failed within the last 500 years. I got sick of seeing the Leaning Tower of Pisa every year. I don't want to see that anymore. So you're going to use the case study using Word, PowerPoint, Publisher, or any other software desired. I want you to do it in landscape format because we're going to put it up on the screen here. So I don't want it to be tall up and down. I want it to be tall left and right. I want to know the following information: the name of the building, the location of the building, the date of failure. Was there any loss of life? And if so, what were the number of fatalities? I would like to see after photos or illustrations of the building after it collapsed. And I would also like to see photos before it collapsed if available. I would like to see video or news report or links if available. And I want to see internet links to more than one source. So that's just kind of the information, but then I want you to actually analyze it or come up with these. This is how we're going to learn from other people's mistakes. One is that, what was the cause of the failure determined by the experts? If they say, oh yeah, they tried to save money and they didn't put enough reinforcing in the concrete, we need to know about that because we'll learn about why that happened and how to avoid it. If they say that they didn't review the shop drawings and the shop drawings changed something that caused something to collapse, we need to know that. Any lessons learned or laws or code changes. So a lot of times these building collapses actually require them to change the laws or the codes to avoid it happening in the future. And then the last question was anyone held accountable either criminally or financially? Did they end up going to jail, or did they have to pay a fine, or did they lose their license? So we're going to try to get all through the presentations on Thursday's class. Okay. It should not be longer than 10 minutes. That means if you find an awesome, because I've got 15 students, and 10 minutes is 2.5 hours, right? So I know some of you are going to be shorter than that. So hopefully we'll get all of them done on Thursday. That means if you find an awesome 1-hour video, we just have to watch little bits of it that you consider highlights. We're not going to sit there and watch the whole thing. Okay. And then you're going to post the PDF of the case study to Blackboard. And so this is how you're being graded. You get 1 point for the presentation. You get 3 points for these items here. Just check the box. Cause of failure determined by experts is 3 points. Any lessons learned or laws or code changes, 2 points. Now, if there weren't any laws or code changes, just say, no, there weren't any laws or code changes because of this. Like if a balcony collapsed in Winona, they might not change the Minnesota code. You would just say, no, there weren't any law. Was anybody held accountable? Sometimes you can find it in the internet sources, sometimes you can't. If you can't, say, I couldn't find any information on that. Case study PDF, layout, design, and quality of images. And I'm going to give you a hint on the layout. If you're showing something on a big screen like that, it should be left to right landscape so that it fills the screen better. Does that make sense? Okay. So I'm going to give you a 10-minute break until 20 to 11. If you want to get your choice of buildings and put it in the discussion board, let me just show you where the discussion board is. You're welcome to do it during the break. So there should be a link here that takes you to the case study. And you're going to type a post, and then you're going to use this format: year, name of building, and location. So I just made one, 1931 Elmer's Mill collapse, Onalaska, Wisconsin. I'll just type in okay, and then you're locked into that one. So if you're the 15th person to do that, you have to read all the 14 before you pick it, because I don't want you to pick the same one over again. Okay. Well, we're going to take a 10-minute break until 22:11. So this is the first time I've used it. Can you see everybody's posts? Can you see the other students' posts? Nathan, I gotta Google your hard rock, cause I think that one might actually be a construction failure where a crane collapsed. Let me just Google that one. I'm gonna let you do that one, Nathan, just because they ended up finding that it wasn't totally related to construction. So yeah, I'm gonna let you do that. That one's kind of a border judgment. You have to, I think, what was yours?
The Massachusetts Pemberton Mill.
Yeah, I think I replied okay on that one. Yeah. They are. This is one of my favorite assignments, believe it or not, because you can learn so much about where things went wrong. And it's not meant to freak you out and make you scared of buildings or scared of doing things. It's more like a lot of times there's so many warning signs that people ignored and ignored and ignored, and they just did that dumb thing. Or greedy.
did the one that I was.
Now, there's some famous ones that nobody has picked yet. So there's still some out there. I'm gonna let you do the one even though it fell down during an earthquake. It
Oh.
turns out it wasn't the earthquake only that caused the problem. So I'm gonna let you do that.
Thank you.
And you took the one I was gonna do.
If you end up like totally can't find something, I will, I can help you, but I'd like you to actually do the research and find your own buildings first. I will only do that as a last resort. No, like, if I have a 20 student, in the class, we have 15 people in this class. The 15th person to select might have a little bit of trouble finding one that's, easily selected. Okay, so if that's the case and you really can't find one, rather than have you not do the assignment, I'll give you some tips, but I'd like you to search and find your own projects. In a couple minutes or so here, and I'll get back into it. I'll get it back into my kind of my first PowerPoint lecture. Okay, I'm gonna take a minute here to see if there's been any new posts that I can look at.
So are you saying you want me to do another different one?
I do want you to do the building.
Oh,
I said okay on my reply, because it turns out it wasn't the earthquake was the total cause of the collapse. Bethany, that's a very famous one. That's good. That was one of the ones that nobody picked. I was gonna tell somebody to pick. Okay. Charles de Gaulle Airport, I remember seeing that one on the news. That's definitely okay. Okay. Again, Jingwang Building, Taiwan.
Buildings around it all stay standing, but this one, come to find out that oil cans in the columns empty.
Well, since that's a new one and I'm very intrigued by that, I'm even gonna look it up. I'm gonna say, okay.
I was reading about it, it's like, whoa.
Okay, that sounds like a good one. That's a new one I've never heard before. Okay. So we'll present these start a class on Thursday. I'm gonna go ahead and do my little PowerPoint and then I'll let you work for the remainder of the time. So let's go ahead and get my PowerPoint up. So try not to work on your case study because this is also another assignment. There's a quiz on this assignment 1.3 courses. So let's go ahead and watch this PowerPoint. Okay. So I'm hoping Star Wars is still a thing among the younger generation. So we're talking about forces and not that kind of force. We're talking about loads and stress. So I'm staying on my Star Wars theme here, just because there's a light and a dark side of the force. There's actually opposing forces, internal and external. So if I apply a load to a body, it's an external force and that's called a load. When I applied a load to something, that internal force resists it and balances it out, and that creates a stress inside the material. So if you apply a force and let's just imagine I applied a force to a tennis ball on the floor. That's not gonna have any internal forces because it's actually gonna move it. But on something like a footing, we don't want our footing to move. We want it to be pushing into the dirt. So that force that we put on there creates a stress inside the footing, which in turn creates a stress inside the soil underneath it. Okay, because we don't want buildings to move when they're under loads. So when we have a force, we can have a load that's applied to a building element that creates a stress inside of the building element. And it's kind of like when you think about your personal life, an external force that's pressing on you creates internal stress inside of you. It's psychological stress, right? I'm not talking about loads, but that's a way to remember the difference between a load and a stress. Okay, so a lot of times we know how much stress a material can take, but we need to measure it by dividing the load by the area the load is acting upon. So the formula is stress equals, now you don't have to memorize this. This is an open book quiz that you're going to take on that. But the formula is stress equals the load divided by the area. And here's an example. If we apply a 3,000 pound load to a 10-inch by 15-inch stone block, what is the stress inside the block? So we have the load, 3,000 pounds, we divide it by the area. So the area of, does everybody understand how I got 150 square inch area? What two numbers did I multiply? 10 and 15, okay? So if I measured this here, this was 10 inches and this is 15 inches, I have 150 square inches. So if I do the math on that, 3,000 divided by 150 equals 20 pounds per square inch, or PSI. Have you ever heard of PSI before? Okay, so that's what that's doing. It's telling me how many pounds per square inch stress is being put on that stone block. So that block is actually being compressed. We're pushing on it. It's microscopically getting smaller. So we would say that that block is developing a compressive strength of 20 PSI. If we were pulling on it, it would be a tensile strength, stress of 20 PSI. So the PSI stands for pounds per square inch. There's also one called PSF. What do you think that stands for?
Pounds per square foot.
Pounds per square foot. Okay, so that's again, you can look this up while you're doing the assignment. Stress equals load divided by area. So when we put a load on a body, there's another thing. In addition to developing the stress, like I mentioned before, maybe you'll be able to see it smush down, or maybe you won't be able to see it smush down, but it will smush down a little bit. And that's called strain. So strain is the change in size of a body caused by external loads. So applying external load causes a deformation. So it either gets longer if it's in tension, we're stretching it out, or if it gets shortened if we're pushing it together in compression, and that's called strain. So the thing to remember is when I put something under stress, it causes a strain where it's actually making it either smaller if I'm pushing on it or a little bit longer if I'm pulling on it. So now here's a practice problem. I want everybody to get their calculator out, or a calculator on your computer out, or your phone. So we measure the stress in a material by dividing the load by the area the load is acting upon. So if we apply an 8,000 pound building load to a 2-foot square by 18-inch thick spread footing. Now we're ignoring the weight of the footing and of the column. We're saying we got 8,000 pounds, maybe it's 8,000 pounds of building and the column and the footing, but all that load, 8,000 pounds, where you see these red arrows, there's 8,000 pounds pushing on the bottom of this footing onto the dirt. And we want to know how many PSF we're pressing on the dirt, because certain soils can only take so many PSF. Like bedrock might be able to take 8,000 PSF, but like mushy clay might only be able to take 2,000 PSF. So we want to know if we're pressing that footing that's 2 foot square, if we're pressing 8,000 pounds onto that footing, what's the soil stress beneath that footing? So I'm going to give you a couple seconds here. And so I gave you two numbers. I gave you 2 foot square and I gave you 18 inches thick. I'm going to give you a big hint. You can ignore one of those three numbers. I'm giving you a 2, I'm giving you a 2, I'm giving you 18 inches. One of those numbers has no impact on this calculation. That's a hint. So if you think you have the number, why don't you raise your hand and I'll just come over and take a peek at it. Yes, and that would be in what? GSF, pounds per square foot. And don't make it harder and more complicated than, there's a lot of people have a tendency to make it more harder than you. So that's why the units is important. So if you did this on a test, you'd also have to write PSF after it. Yes. Yep. Yep. Yeah, good. I'm gonna go ahead and show you the calculation here. So 8,000 pounds, which is my load. My area is 4 square feet because 2 times 2 is 4 square feet. And I'm asking for the answer in pounds per square feet. So that's why I want to do it with the 2 square feet. The 18 inches is irrelevant for our conversation here, right? If that was 36 inches, the answer would still be, if I was 8,000 pounds, it would still be 2,000 PSF. That makes sense. The only reason, like, now let's just say that it's not totally irrelevant, because if the footing was only an inch thick, the concrete wouldn't spread the load out from the column and the column would punch through that skinny little footing.
So it's about the disbursement.
Yeah, what we're assuming is that concrete's got enough reinforcing in it to spread the load out evenly over that footing, okay? But that's actually a real number, because if you don't do a soils report, you should assume 2,000 PSF for the footing, because that's like the lowest soils you're typically going to find around here. Unless you're building in the middle of a swamp or something, then it's probably even going to be lower. But if you don't have a soils report, you typically assume 2,000 PSF is the most that the soil will take. Now, let's imagine my soil will only take 2,000, and that number would end up being 4,000. Say I'm trying to drop 16,000 pounds on there. I just have to make my footing bigger, right, to spread that load out so it doesn't push more than 2,000 PSF onto the soil. Okay, so now let's talk about some other basic concepts. All forces on a building are either pushes or pulls, or a combination of the two. So a pushing force is called compression. A pulling force is called tension. When you push on a door, your arm's in compression. Because if you can imagine, if your arm was made out of silly putty and you pushed on a door, your arm would get shorter. If you pulled on a door, your arm was in tension. If my arm was silly putty, I was the plastic man, and I pulled on a door, my arm would get longer. So that's pushing and pulling. So in a tug of war, this is a simple example. Is that rope in compression or tension? Let me say the answer out loud.
Tension.
Tension. right? Because it wants to get longer. They're pulling on it, that rope's in tension. Now we're gonna use some building elements. Parthenon's columns. Are they wanting to get smaller or longer because of the loads on them? So are they in compression or in tension? Compression, right? Because the weight's on the top's kind of mushing them. If they were made out of silly putty, it'd be mushing them smaller. So this is one of the famous building collapses ones. I don't know if anybody's picked it one. The Kansas City Hyatt walkway collapse. It had a walkway that was held up by steel rods. Are those steel rods in compression or in tension? Tension. They were hung from the roof. And that's where that walkway was held on. How about the stones in an arch? Are those in compression or tension? Compression, right? Because they're pushing down, they want to get made smaller. What about the cables in the Golden Gate Bridge? Tension, right? Because they want to get stretched longer with under the load. Okay. So now we're going to do, just like we did compressive stress before, now we're going to do a case study or an example with tensile stress. And the only complication I'm adding, the stress equals load divided by area, that's still the same, but I'm gonna do a circle. So this is a bridge that's held up by cables from this mast here, and those cables are in tension, and so we need to calculate the tensile stress on those cables. So I want to know what the unit stress is created when 6 tons is suspended. I'm going to say they're rods, or they could be cables, on a 1/2-inch diameter steel rod. So let's look at the math here. Stress equals load divided by area. So we know what the load is, 6 tons, a ton is 2,000 pounds, right? So we know the load is 12,000 pounds. So here's 1 ton equals 2,000 pounds, 6 tons equals 12,000 pounds. So that's the number that's going to be in the load part of it. Now, we have to figure out the area of a 1/2-inch diameter circle. And so I'm going to do a little bit of math review here. How do we find the area of a circle? Pi r squared. Do you ever watch the Three Stooges? Okay, so they have a little skit where they go, pi r, the guy's a teacher or professor, and he's like, well, pi r squared. And then one of the Stooges goes, no, pi r round. Because you don't make square pies. But anyway, it's pi r squared is how you get the area of a circle. So that's what is showing in the lower right there. So r equals radius, which is half of the diameter. So here, if my diameter is a 1/2 inch, my radius is only a 1/4 inch. Now, if your calculator has the pi built in, it'll do it to more digits, but I just do 3.1416. Some people just do 3.14 times a 1/4 inch times a 1/4 inch. So that's pi times radius squared. And that equals 0.1963 square inches. So then I just do the math here. I take 12,000 pounds divided by 0.1963 square inches. And I end up with 61,130.92 PSI tensile stress. And believe it or not, that would break that rod. Okay, so that's more than the steel can carry. So that's why, again, if you think about liability and getting sued and all that, whoever's doing these calculations for that bridge, or like if you look at the bridge going over the Mississippi, they need to know these calculations have a factor of safety and a margin for things rusting and all that. We would never size it up to the breaking strength of steel. We would always leave ourselves a factor of safety. But that's how the math is. It's a very simple calculation, but what mess students up was they wouldn't calculate the diameter properly on a circular shape. So let's do a practice problem. This time we've got this person lifting this weight, and it's not a 1/2 inch diameter cable, it's a 1/4 inch diameter cable, and she's lifting 150 pounds on this 1/4 inch diameter cable. So we've got stress equals load divided by area. We know what the load is. You're going to have to figure out the area of the 1/4 inch diameter steel cable, and then you're going to do the math and tell me what the tensile stress is in the cable. So if you think you have an answer, I can see my next slide here. I'll see if you're in the ballpark or not. I know everybody's pi is different on their calculators, so I'll take that into account. So raise your hand if you want me to check your answer. So this one, we're going to end up with an answer in pounds per square inch. Yes. What it is. Give you a few more minutes here. If I could give you a little bit of a hint when you do this on the assignment, write it out and show your work. It's one thing to just type numbers in the calculator and then just give me the end number. But then if you made one little mistake, I can't give you partial credit because the answer's wrong. And you might have had everything right except one, like hit the wrong button on the calculator. So it's better to show your work rather than just type a bunch of numbers in the calculator and hope you end up with the right one. We'll wait a few more minutes, see if anybody wants to hazard a guess at this one or show me their attempt. I'll show you how I did it. Any last minute guesses here? Okay, I'll show you how we did it. So again, the big hardest part of this is to find the area of a 1/4 inch diameter. So radius is half of the diameter. So what's the decimal equivalent of 1/8 of an inch? 0.125 inches. Okay, so you take 3.1416, which is pi, 0.125 times 0.125, you end up with that little number for the area in square inches. And then you take the 150 pounds and you divide it by that little number, and you end up with 3,000 ballpark 55.77 psi, and that's a tensile strength. That'll make sense, yeah.
I thought when I did my calculation, I did 0.25.
Oh, 0.25, that's a 1/4 inch, not point. It's because like if you look at the little diagram here, diameter 1/4 inch is that, it's pi r squared. Radius is half a diameter. Okay. Okay, now let's talk about strength of materials. Strength of materials is resistance to breaking, and it's measured by the stress. So above those stresses, the material will break by snapping in tension or crushing in compression. So now we know what PSI means. Now you can know, like, remember I told you in materials class that concrete is terrible in tension. That's why we have to put steel into it. Remember all that? I see you nodding head, so I'm glad you remember that. You can see it can take 3,000 PSI in compression, but only 500 in tension. That's why we don't make ropes, tow ropes for our cars out of concrete, right? Because it would break very easily, okay? Limestone, you can see, is extremely strong in compression, but it's very, very weak in tension. Same thing with brick. All those heavy masonry materials are typically terrible in tension. Wood, believe it or not, is very strong in both ways, but it's nowhere near steel. Steel takes 60,000 PSI to snap it, and it takes 60,000 PSI to crush it. So steel is amazingly strong. But believe it or not, your femur bone is up well past wood, well past concrete in compressive strength. And it's all about half of what steel is. Now, the human hair is just so skinny, you can't really measure it in compression. But in tension, it will take 28,000 PSI, just your hair. And I know they've done tests on spider webs in tension, and it's pretty amazing what some of these natural materials can take. So you can see why we have to do reinforced concrete, because if we have any tension in that member, we're going to have problems with unreinforced concrete. So what is a load? A load is a force that the building structure needs to resist, and they are divided into dead loads and live loads. So the dead loads are parts of the building that are the building and things that are permanently attached to it that don't move. So like the walls are a dead load, the floors are a dead load, the roof structure is a dead load. All that's dead because it doesn't change and it's part of the building. The live loads are things that are applied onto the building that can move. They're live. So like all us people, we're live loads because we could all go and stand in that corner packed together as tight as we could, or we could spread out here. We could have this room totally filled with people, or we could have no people. So it changes, right? Same thing with like rain loads. You could have no rain, ponded on the roof of your building because your roof drain clogged up, or you could have a foot out there. If all those roof drains clogged up, we could have a foot of water out there. Okay? We could have no snow on the building, or we could have 6 feet of snow on the building. So that's a live load because it changes. But the building has to resist both dead and live loads. So here's the dead loads. They don't move. It's the weight of the building and permanently installed components. They don't move or change. They're dead. That's also called self-weight. So here's a little chart that shows how much all these various building materials weigh. And now you know what PSF means. That means that a 1 inch of gypsum wallboard thickness weighs 5 pounds per square feet. An exterior stud, exterior wall structure with studs at 16 inches on center with brick weighs 400 pounds per square feet. Did I calculate this on a house? When I was designing houses, did I figure out how many sheets of plywood are on the roof, how much my plywood weighed, how much the nails weighed, how much the trusses weighed? No, I did not. There's typically, you calculate the dead loads on a house for rules of thumb. So like a 15 pounds per square foot load typically covers a floor dead load and a roof dead load. Okay. But on a commercial project, the engineer did calculate it because it wasn't as standardized as the house is. Like this floor could be 2 feet thick of solid concrete, or it could be that hollow core precast concrete, or it could be concrete with pans in it, like I showed you over at the Com Center. So the engineers will actually calculate how much your building weighs. They will calculate the dead loads for you. So we know now dead loads are dead. Building, things permanently attached to the building, doesn't move around. The other one is live loads, includes us and our stuff, rain, wind, snow, earthquakes. They're loads that change and can move. So your building is designed to take a combination of dead loads and live loads. So where do we find our live loads? We look them up in our friendly building code. So a floor has a different live load than a roof. Now this is a live load for floors, but they're given in pounds per square foot, right? PSF. So here, let's look at an example. A movie theater assembly lobby has a live load of 100 pounds per square foot. In an apartment, residential apartment has a live load of 40 pounds per square foot. Why does the code make you do 2.5 times more load on a movie theater lobby than in an apartment? Or people, like the movie gets done, or like say the people, it's like a movie everybody wants to see and they're all waiting for the movie to get up because there's only so many seats available. That might be standing room only. It might just be packed in there. You could hardly walk through it. So you have to have a higher live load because you have so many more people packed into it. So you see, if you have an assembly building where a bunch of people are gathering together, our live loads are going to be much higher. You can see here on fire escapes, that could also be, if there's a fire, I guarantee you that fire escape's going to be packed with people. So that's got a live load of 100 pounds per square foot. So the code will tell you what live loads you need to use for what kind of building you're doing. So now let's look at a real world scenario. Code minimum live load for a house or apartment is 40 pounds per square foot. That's obviously not 20,000 years in the future. It's supposed to be 2012. Or maybe it's either 2012 or 2021. There was a crowded house party in La Crosse where the floor collapsed. Let's see if this link still works. So that was, I guess it was in 2012. So they had a big house party. They found multiple beer kegs where the floor had collapsed. They heard loud music, but didn't think much to it. He was used to a lot of noise. He went downstairs and found the street full of fire trucks. The floor of a second floor neighboring apartment collapsed. 50 people were in the apartment when a 30 by 30 foot area of the second floor to the rear of the building caved in. So 300 people were treated at the scene. They ended up condemning the building. Okay, so that's a real world scenario. Now let's go back and look at my PowerPoint. Do some math. So they said a 30 by 30 foot area with 50 people in it collapsed. Why do my monitors keep switching off? Okay. Is everything constantly going on and off?
Just started.
The Zooms are still good, okay. 900 square foot room with 50 people at 200 pounds each, and let's assume 1,000 pounds of furniture. So we have 50 people times 200 pounds each, that equals 10,000 pounds, and then we add 1,000 pounds of furniture. That equals 11,000 pounds total live load in that room. It's divided by 900 square feet, so if those people were evenly distributed, that loading would be 12.22 pounds per square foot, which is the code minimum is 40. So that shouldn't cause the floor to collapse, all things being consistent. But that assumed the people were evenly spread out. Have you ever been in a party or a house party where the people were literally packed into one area? Like say there was free beer and it was running out and they were all packed around the keg. Let's imagine they were all packed around the keg. So assume the people weigh 200 pounds each and they're jammed together. So like if I would draw a square on the floor, if I was jammed together, it'd probably be about 2 square feet, right? Because like my shoulders are about 2 feet wide and probably about a foot that way if we were just packed in there. So let's take a 200-pound person that's taking up 2 square feet of area. We end up with 100 pounds per square foot. Now, interestingly enough, remember what we found for the lobby of the movie theater? It was 100 pounds per square foot live load. And that's what they're figuring. They're figuring on 200-pound persons jammed together shoulder to shoulder. You're never going to get more probably than 100 pounds per square foot on the floor. So in that case, if they were all jammed together, then I can kind of understand why it might collapse. There's also something called a concentrated load. So say your roof live load is only 30 pounds per square foot, but you've got a big 300-pound roofer carrying a bunch of bundles of shingles about there. His feet are only like half a square foot and he's got 500 pounds worth of stuff. So it's also got to take what's called a concentrated load. Okay, so your roofer walking around your roof carrying a bunch of shingles, you have to take a concentrated load of 300 pounds. See, so it says all roofs subject to maintenance workers, awnings and canopy. All roofs subject to maintenance workers have to take a concentrated load of 300 pounds. So when the engineers design your building, they're not only looking at your distributed live load, they're trying to figure out, is there going to be a concentrated live load? Like, for example, if I'm doing a factory, let's imagine we had forklifts or that little lift out there, right? That lift that's going up and down to service the green wall. That's going to be a concentrated load, right? Because that's not like a normal load spread out over a big area. That's a big, heavy piece of machinery rolling around. And I'm hoping when they designed this building, they designed it for that concentrated load going around. Okay, so let's talk a little bit, get it down into houses. The Wisconsin code, and we'll have a code assignment in the second 7 weeks here, is 40 pounds per square foot live load from the Wisconsin Uniform Dwelling Code. I typically assumed a 15 pounds per square foot dead load for a wood frame floor for a house. So when I was designing my floors, I took the dead load plus the live load, and I ended up with 55 pounds per square foot when I did my calculations. Okay. 2 more slides. Gravity loads are downward uniform forces on all structures. So the weight of the building, that's always going down. It's not ever pushing off to the side because all of us are being pulled by gravity. That force goes to the center of the Earth's core. So like if you're in Australia, you're still going downward to the center of the Earth's core. So there are such a thing called lateral loads, which produce a sideways motion. So if I have wind, that's blowing on the side of the building and it's wanting to tip the building over, that's a lateral load. Lateral means sideways. If I have earth, like on my building foundation wall in my basement, that's pushing that wall sideways. That weight of that dirt wants to tip that wall over into the basement. Okay, so that's a lateral load. Earthquakes move buildings in all directions, but since buildings are typically weaker side by side, they are designed for earthquake lateral loads because that earthquake can shift the building left and right as it shakes. Now, this might kind of freak you out, but believe it or not, wind can pull up on a building, and it's called uplift. So wind can create a negative pressure suction, which creates uplift on a roof. And here's a little diagram. So as that roof, the wind comes over the roof, it kind of makes the shape like an airplane wing as it goes over the thing, and that creates lift, just like that shape of an airplane wing creates lift with the wind blowing over it. So it will actually lift things off of your building and a high enough wind. So if you look out this window here, you're going to see we got a bunch of rocks out on our roof there. That roof is a loose laid ballast. That's ballast on our rubber roof. The rubber roof is not glued down when there's ballast. It's great because there's no screws, there's no holes, there's no glue. It's just laid out there. If we didn't put the stones on there and there was a strong wind, it would balloon up just like a balloon because that suction would suck it up. And it would look like a half of a balloon out there. There'd be like a big tent of that rubber roof, and it would eventually stress the roof and fail it. So kind of, this is an exaggerated shape, but that roof would want to pull up in that low pressure area from the wind going over the roof. Well, this is just kind of interesting because it shows roofs coming off of buildings, and you're going to see a lot of times they come up. Now, sometimes they just blow off sideways, but sometimes they come up. And then there's other cases where the wind gets underneath the building, like say it's an open structure, and it'll blow the roof off from the inside because that internal pressure. So I'm going to show you some roofs coming off of buildings here. First 5 minutes of this video. Crap. Okay, I'll find another version of this. Maybe later we'll show it to you. Okay, so let's show you the assignment for this, and then I'll let you work on all your assignments. You have a structural failure case study, work on that first. This assignment is just a Word document, and then you just answer the questions on it. Now, there's a fair amount of questions, but they should be fairly straightforward if you have that PowerPoint open and like look at the examples. So let's just click on that to show you what it is. So I have you figure out some load things where, load divided by area, figuring all that out. I have you figure out whether these things are dead or live loads. Remember, dead loads are the building and things permanently attached to it. Live loads are movable items that change. And then I want you to answer whether these are gravity, lateral, or uplift, these forces on the building. Okay, so that's due a week from today. So do not do this now. You should probably be working on your structural failure case study, or you can go home, I suppose, if you want, but I'm gonna give you the rest of the class for work time. Any questions? And then there's that one little assignment about watching that video of the design meeting and answering a couple questions on it. Okay, that's all I got. Thank you.
Number.
Can somebody else beat me to the punch of this? Are you kidding me? Plaza was a minute before you. Why don't you pick since you've done two of them, why don't you pick the Hyatt Regency Skywalk collapse? That's a classic, good one.
Okay.
So put it on the case study thing so nobody else picks it.
Family's farm and it's barn. The hay barn, the entire upstairs got lifted.
So it did. It got lifted up and carried away.
It was, I don't know, 500 feet across the road. It
Seriously.
was one piece and it just lifted it.
I gotta find a video of roofs coming off buildings because it was a fun video to watch. I'll find another version of that.
Nature's a little wild.
Yeah.
The opposite of any word platform.
Okay, if you guys don't mind watching, I found just a very short.
What are the word?
So this is actually a test chamber that they did once the hurricanes hit Florida. That they built one with the old code and then they built one with the new code after the hurricanes, that they made it so that the roofs were left likely to blow off. Let's see if this is, so you can see it actually comes up when it gets blown. It won't slide off, it kind of lifts up. You can see it here. It lifts up and then the wind takes it and blows it away. So that one on the left was the old code. And then after one of the big hurricanes, they did a new code that required like connectors that held the trusses down onto the roof. Okay, so I got. So Duncan, just so you know, it's Hyatt, like the Hyatt Hotel,
I
not
know.
Hyatt. Yeah.
Message coming in. Thank you.
Did it work this morning and it just stopped? It didn't work?